working.
It should be walking.
All right. Well, sorry for the late start, but let's get started now.
Not very late.
It was my fault, so don't worry.
Like 4 minutes late.
So today we're very happy to have Michael Kruse. Michael is, of course, famous for his work through many years in Lattice QCD. And we're very happy to have him here today. And he's going to tell us about his recent paper on the standard model on the lattice.
Thank you very much. And Misha has actually heard this talk before, so hopefully he won't mind too much.
Want her to hear it for the second time.
Yeah. Okay, so why would we want to put the standard model on the lattice in the first place? Well, we know that neutrinos exist with one-handedness to them, left-handed. And the other thing, one of the purposes, well, first, the lattice is good for calculations, but I'm not going to be interested in that here. It's a way of defining a field theory. Strong interactions are defined, one way to define them is the continuum limit of a lattice theory. So what I want to do is see if we can do this include the weak interactions here. So I'm going to try and set up a formulation which is on a lattice with an exact local SU3 cross SU2 cross U1 gauge symmetries. I'm not quite all the way to defining the theory, though, because there's a couple problems. I'm going to need to use the Higgs mechanism. And Higgs is not asymptotically free, so we don't know how to take a continuum limit for the Higgs field. And the same thing for the electrodynamics. Now, the electrodynamics you could probably fix up by going for some kind of unified theory like SO10. And the Higgs you might be able to do with some kind of composite Higgs and with some more groups. But I'm going to try and stay entirely within the normal standard model. Nothing extra. The approach is based on some very old papers of Swift and Smith in the early 80s. Now, this never quite panned out, but I'm really going to build on it and show you how you can make it work. The problem, I think, is mainly that they tried to do it just with the left-handed chiral fermion. That was all they wanted to get out. In order to make this work, we're going to have a very complicated interplay of the weak and the strong groups. And this is going to require me the formulation to include a whole generation of fermions. And I'm also going to be using the pseudo-reality of SU2, which is basically the fact that the antiparticles of left-handed doublets are also doublets, but they are right-handed. And so we're going to have to bring the right-handed antiparticles in. This is going to wind up with some interesting phenomena, like the fact that in the weak interactions you can have baryon decay, because we're going to be mixing left-handed things with right-handed things. Now, one of the problems with trying to do it with just a single chiral fermion is a theorem of Witten from years ago. He showed that a single chiral multiplet is an inconsistent theory for SU2. There's an anomaly there, which will be discussed in a couple of places here later on. He basically showed that I only had a single fermion with chiral fermion. You could do some transformation in your gauge fields, which will take the fermion determinant to its negative, and that's all it does. And so you wind up with the partition function just vanishing. So I'm going to have to bring in more doublets than just the one. And then for the standard model, I need to bring in the strong doublets too, in addition to the neutrino. And in order to do this in a way which doesn't break the strong interactions, you'll see how I'm going to be forced to use the entire generation. I'm going to need the Higgs to give particles masses, and I'll do that in a normal way. But the Higgs also lets you get rid of the doublers, which are so famous in the lattice approaches. But what's going to be particularly interesting is that how the 2 vertex comes along and forces you to have proton decay in the theory. It's extremely small. It's not something you can ever measure, but it is there in principle.
So sorry, so just so I understand, so you're going to have you're going to have an extra chiral generation, so you'll have 4.
Well, it's a question whether you call them. There's going to be 4 doublets. There's going to be the 3 colors of the up and down quarks, and then the neutrino as well. So there's going to be 4 doublets involved. Now you can call it another generation if you want, or another. You can think of Patti Salam if you want,
Yeah, exactly.
but that's what's in your mind. But I don't really use that. Now, one of the things I wanted to discuss is lattice topology. The physics that comes about becomes instantons. They're very important in strong interactions because they're going to give the eta prime its mass. And that's pretty well understood. But we're going to see that when you have SU2 instanton, you generate this proton decay. And it's very interesting to see that there's actually a small proton-positron mixing and neutron-neutrino mixing. It's tiny, -1 over alpha, so it's perturbation theory is just fine for the weak interactions, but I'm interested in the principal way of defining the theory. And this is another interesting thing is on the lattice gauge fields are all simply connected. You don't have topology. Typical lattice fields in the configuration are in fact not differentiable, so you can't really define the topology very well. So we're going to find some chiral modes, but they won't be exact zero modes. They won't be robust as zero modes, but we'll see how that works later. Okay, so as I said, I need to take the full generation together. So I'm going to start with 8 4-component fermion fields on my lattice site. So every lattice site has 8 fermions. So these are the up quarks of red, green, and blue, the colors. The down quarks are red, green, and blue. And I'm going to have a neutrino and an electron.
And each of them corresponds to 2 Weyl fermions, right?
You can think of it that way, yeah. Yeah.
Okay.
But I'm thinking sort of more common.
So this would be the 16 of SO10, right?
Exactly. In fact, this is SO10 kind of smells at you through this whole thing, but I won't include all the leptoquarks and all that.
When you count in terms of Weyl spinners, when you count in terms of Weyl spinners, this is just the 16.
Yeah,
It is exactly 16. So that's I actually like SO10 as a formulation for this, but I don't need it all. Okay, so these are the color indices R, G, and B. So the up and down quarks come in 3 colors. And these are all going to be, I'm going to think of them all as Dirac fermions. So they've got both, there's a right-handed neutrino, although it's not going to interact. And then the other field we need on every site is a Higgs field. So we'll have a complex doublet of H1 and H2 on the sites. Okay, in addition to my fields on the sites, I've got to have my gauge fields. And I'm going to do that in totally standard lattice gauge language. So on every bond, there's going to be an SU3 matrix, an SU2 matrix, and U1 matrix. So there'll be some element of SU3 on every bond, an element of SU2 on every bond, and a phase on every bond. And as far as the gauge fields are concerned, I'm going to just use standard plaquette actions. So you multiply the things around plaquettes. That reduces the FF dual and the Nye continuum limit. And nothing fancy there. But the way the strong and the weak groups couple to the fermions is somewhat different. So for our single generation, we've got 2 vector-like strong triplets, up quark and down quark. But we've got the 4 left-handed weak doublets. So there'll be the red one with the red D, left-handed, green one, U with D, blue one with U and D, and then the left hand and the left-handed multiplet. Okay. And I'm perfectly happy to have any questions you want as I go. So we want local gauge symmetries.
I have a
That's a
question.
question.
Is this the simplest model where this idea can work, or is there some simpler model, like in 2 dimensions? Where you can try all this?
I don't know of any simpler model than this. You got to have at least an even number of doublets in order to make it work. Now, if because of Witten's theorem.
That's a 4D thing. You could go to 2 dimensions there, Carl.
Oh, in lower dimensions?
Yeah, simpler models, where we know more. Like
I don't know.
3450 model.
Yeah, the 345 model.
Yeah. Does anything like that work there?
I don't know.
Okay, fair enough. Just curious.
Yeah, I don't know.
Okay, that's okay. I mean, it's clearly
Yeah.
not in the line of the talk. So that's
Well, that's all right. I mean, I gave this talk in half an hour in Florida, and I got an hour here. So, but it was not. You had another.
No.
Okay. So I'm going to require an exact symmetry on every site. That if I take the up and down triplets and multiply them times an SU3 matrix, that should be an exact symmetry. So I'm going to have an SU3 matrix. The gauge transformation will be defined by having SU3 matrices on the sites. But the weak group does it differently. It's only going to act on the left-handed part. So 1 minus gamma 5 over 2 with this SU2 element. But the right-hand part doesn't have any SU2 element in it. And that's going to apply for all 4 of these doublets, the blue and the left-hand doublet. And these gauge transformations will act on the gauge fields as usual. So a SU3 matrix on a bond will get multiplied by this local symmetry on the left side and multiplied by the local symmetry on the right. And these symmetries are independent on each side of the lattice.
Excuse me, Michael, you mentioned that it's a problem with the Higgs because it's not asymptotically free, right?
Right.
But U1 is also not asymptotically.
That's right. So I would say U1 is a good argument for going to SO10. But so those are the 2 things I have not solved. Now the Higgs, there's several things you can think about the Higgs. One, there's been a lot of speculation of the Higgs is not asymptotically free, but it gets driven to such high momenta that you have to worry about gravity. And so I don't know. That's another thing.
Forget about it.
But for this point, I'm just going to try and have the symmetries I want on the lattice. And but yeah. Now the weak SU2 group also acts on the Higgs fields. It's the SU2 doublet. So I take my SU2 doublet of Higgs and multiply by the same site on this matrix on the site, symmetry matrix. Now, SU2 is pseudo-real, so the complex conjugate of any SU2 element is related to the element itself by putting a couple tau 2s in there. These are the usual Pauli matrices. Which means if I take my Higgs field and multiply by tau 2 on each side, which gives me basically minus H2 star, H1 star, this transforms exactly the same way. It's also a doublet. And it transforms under the SU2. So H prime also transforms by the same way as the original Higgs field did. So that's going to be kind of important. Okay, now here's our 8 different fermion fields here, which is the half of the 16. And these are all going to have hypercharge. And for this, I just copied this out of any of the standard books on the standard model. So each one of these gets a hypercharge from the book, which is related to the physical charge on that particle plus or minus 1. The 2 is annoying. I wish it wasn't there, but that's a different convention. Some people do with a different convention. And then it would be Q plus or minus a half. And the Higgs field itself has got hypercharge 1. And then when I go to the complex conjugate of the Higgs field, I get minus 1. And all of my gauge fields don't know about hypercharge. They're neutral. Now, an important feature of all this game is these 3 symmetries all commune with each other. The weak group doesn't change colors in any way. The strong group doesn't break the weak chirality. The strong group rotates left-handed guys into left-handed guys, right-handed guys, right-handed guys, but it doesn't break that in any way. And if you go back and look at the hypercharge assignments, any multiplet, by multiplet I mean those these all have the same hypercharge. Okay. Now let me remind you again of Witten. He said that you must have a even number of weak doublets, which we do. I don't know if you can get away with 2 anyway, but we have 4, so that's nice. What he showed is that you go through field space, the eigenvalues of the Dirac operator can move around, and you can turn the Dirac fermion determinant into its minus. And so therefore the partition function just vanishes with just a single generation. It's kind of related to the 2 vertex, because the 2 vertex is going to be flipping spins. And if you only have left-handed spins, there's nowhere to flip. So what we're going to do is use the conjugates of other doublets to flip things into. We'll see how that goes. Now, for each of my doublets, psi transforms under SU2, and the Higgs field also transforms under SU2. So you can combine them together into something which is SU2 gauge invariant. And it should be more specific. I mean, we're talking about the SU2. So this combination of the Higgs with a left-handed particle, so we take H1 star, H2 star with that 2. This is gauge invariant under the local SU2 symmetry, not SU3. But we've got 2 different kinds of Higgs. We got this and the one which is the conjugate one. And this is also a gauge invariant combination. So for each doublet, there are 2 ways to form SU2 gauge invariant states. So one way to think of this is we should really think of the physical left-hand particles as being composites of the Higgs with the their thing.
Excuse me, in the second line in brown, shouldn't you eliminate the asterisks from H? Because H with asterisks minus H2,
You're right.
H1 is a doublet, and you need anti-doublet.
Yeah, you're right. You're right. That's the trouble. You work on these slides, and it's always impossible to not make some mistake somewhere. You're right. This should be yeah, because these are both the complex conjugates, and these should not be the complex conjugates. Yeah. All right. Just look what I wrote in the paper. So, but basically, the physical left-handed particles, you can think of them as being a combination of the Higgs with the bare quark field, or quark or lepton field. And I'm going to I've got to take out any vacuum expectation value. So the physical electron is really a bound state of the Higgs with the lepton field. And the physical neutrino is the other combination. And you work out the charges. Remember, the Higgs has a charge of 1, and this has got a, whatever it had, I guess it was anyway, it works out to be the right thing. And the same thing with the quarks. The physical quarks should be a combination of the Higgs with the left-handed quarks. Should put an L index in here, I guess. And they'll have charge 2/3, and these would have charge 1/3. This is kind of like in perturbation theory, what you would do is you would work in a what's called a unitary gauge, where you point the Higgs in some particular direction. But in the lattice game, Higgs is not going to be pointing any direction. It's going to be twirling around like mad. The fermion fields are going to be twirling around it like mad in SU3 space, but this combination doesn't twirl. So it's a lattice way to write the unitary gauge.
So here, what do you mean exactly by physical? What do you mean by physical?
Driven by,
It's gauge invariant combination, so that's,
so it's because
That's
it's,
the definition of the physical.
because I'm not going to be fixing a gauge anywhere. So the gauge is fluctuating like mad in the lattice game.
But you care only about SU2, right? So you don't care about U1 or so.
Well, the U1 is in principle doing this kind of stuff too. But that doesn't seem to be, at the moment, I'm basically holding the U1 and the SU3 kind of fixed. They just kind of factor out of everything.
Can I check my understanding of what's happening on this slide? Is this just the total complementarity idea, where the statement is that for everything that we have in the standard model, all of the quarks, whatever, there's a way to write interpolating operators for them that are invariant in their SU2?
Yeah, that's what
That's
we're
what you're
doing.
doing.
That's what we're doing, right? Something which is invariant under.
you can also add SU2 gauge bosons.
Yeah, you can even get a doubly boson.
You can.
Yeah.
W and
Yes.
Z.
Yeah, well, they come in there next.
Before V,
Yeah.
or Z, you
Yes.
can make it.
We can do that.
But to this end.
Oh, wait, actually, I have two slides on.
From both
Yeah.
sides.
Yeah, I know the story. I was just making sure that this is what's happening.
Yeah, that's. Yeah, we'll get to the gauge bosons in a moment. But as you say, you can do the same thing with them. So to generate a mass term, we use these boundings for the left-handed side. So we get a left-handed doublet, which does not rotate under SU2. And then you can mix that with the right-handed part, which doesn't have any SU2 part. And so this is the way you get a mass matrix. And this can be a 2x2 matrix because these are both doublets.
Can I ask a very silly question? What do you mean by V in this context?
What do I mean by?
V? How do I mean like?
It's a constant.
But
Well, V is kind of this field's got some large vacuum expectation value, which is swirling around like mad on this gauge symmetry. But
so,
you really need to.
but
I mean,
to
we know-
calculate V, you need to calculate something using the lattice Monte Carlo calculation, and that somehow goes back into the Lagrangian. That's what I'm confused about.
In the Lagrangian, you have to write Lagrangian for this Higgs, which is the usual self-coupling of the Higgs with a quadratic term. And phenomenologically, there's a known value for that.
Of course, yeah.
And so I'm assuming that we've done that standard thing with the Higgs field, except that now it's something which is spinning around in gauge space.
I guess I'm confused because normally, to the extent that that makes sense, I think of that as the square root of some, whatever, as some expectation value. And I'm not normally allowed to put expectation values in my bare Lagrangians, which is what I think you're trying to construct.
And that's what I'm trying to get around, that Higgs does not have an expectation value.
Exactly,
Because it's twirling.
exactly.
And that's I'm trying to build it in here. So, but the Higgs does not have an expectation.
That's right, because it's gauge charge analysis theorem.
No, it's kind of implementation of the Higgs regime. We know that in the standard model Higgs regime, there is a Higgs regime.
Yes.
Of course, the point V equal to 0, it's the point where it disappears.
I'll have other questions about that later, but I want to see.
Oh, good. But
Psi R is a SU2 singlet, right?
This combination is an SU2 singlet, yeah.
No, Chi-L is doublet, Chi-L.
Oh, it's a
is
doublet, but
SU2
it doesn't
doublet.
transfer under the SU3
But
gauge
the-
field.
Okay, Psi-L, I'm sorry, Psi-L is doublet, but Chi-L is already singlet, right?
Well, there's two components here, so it's got two components, but it doesn't transfer. This transfer is the same as the right-handed thing. It doesn't under the gauge transformation.
Yeah, that's what I was asking,
So
because
trying to find a combination which doesn't transform under the SU2.
I understand. So you have still two fields, psi, right? But they do not transform under local transformation,
That's
right?
And
Okay.
so, and we're combining them with the right-handed parts which don't transform already, and this combination doesn't, so the whole thing is
I
gauge.
understand.
So that's,
But can you think of this, because it's a composite, so that it's a bound state of, right? And so
Yeah.
this is just dimensional analysis, you have to have some constant out the front.
oh, probably, except in the lattice, we always work with dimensionless things. Well, there's a V up
Because
here,
you're
which
putting
has got
together
some
a
constant up here.
boson with a fermion, so you need a constant out the front.
No, you see,
It could be the lattice spacing.
it's
Yeah, okay.
There's
yeah,
always a
yeah.
lattice spacing around
Yeah.
for thing, yeah.
also, it's not quite a bound state in the usual sense. That's because Higgs field is spread over the vacuum.
That raises the big question of what do you mean by bound state? Yeah, how do you
Well,
define
let's
bound?
say it's treated as an operator producing the visible, well, quote unquote, the visible object.
Yeah,
Because it's already gauge invariant, at least under SU2. It's still not gauge invariant under SU3, but SU3 is in this confining strong coupling regime, and their confinement.
Confinement takes care
care
of it, yeah.
So in the confining theories, all fields rotate, as Michael wants to say, like crazy over the entire gauge group.
Now, once we've got this other combination which doesn't spin, you can use this other combination also in the Wilson term. Now, I guess since this is not really a very latticey audience, probably have never heard of the Wilson term.
Some of us.
But you just take the usual Wilson term, but use this composite combination. Just set it up. This formally looks like a irrelevant operator, psi bar d squared psi. And the idea is that this is only important at very large momentum in order to cutoff. So what it does is it drives the masses of the doublers up to their cutoff. And I guess I will say a little more about that in a minute, but once you start shoving things up to the cutoff scale with these more dimensionful things, an additive renormalization is there with Wilson fermions, and that's required. You have to tune masses to zero with the Wilson formulation. Now the bosons, as Misha was saying, you can construct them by taking the SU2 matrices on the bonds and throwing in these factors of the gauge. So you get something which doesn't spin anymore, these cancel the spinning of that. And this combination has charge 1, and there's another combination which has charge -1. There's two combinations which have charge 0. One of them you should think of as being the hopping term for the Higgs. This is how the Higgs gets from one site to the next. And the other one is the Z. And they in general can mix. And so I don't know how you can pull out which physically the Z from this combination of things.
Can I ask a question about the previous stuff? Actually, the slide before that about the Wilson fermion. So here I have several questions. Sorry, but for additive mass renormalization, what is the mass parameter that you dial? It's very hard to write mass terms
Well,
That's the biggest-
the original ones are, everything's going to get shifted. And so this mask here is going to have an additive correction to it.
So normally we say there are no gauge invariant mass terms in chiral gauge theories, but you are constructing one using this.
That's right. So I'm saying the fact that the neutrino is very light is tuned. It's not natural in this game.
Okay, in and of itself. But then I have another question. Like, imagine, like, with the standard model, I can imagine playing with the Higgs potential. And I can either drive it into the deeply Higgs regime, which we have in, well, fairly deeply Higgs regime that we have in nature, or I can imagine dialing it so that the Higgs VEV, which of course we understand is only in quotes, is basically zero.
Yeah, you can't.
Well,
That's the whole point.
In your model, you can.
The unconfined, that phase doesn't exist. There is no phase without.
if I go to high temperature, that phase almost.
Oh,
exists.
okay. Temperature is another question.
But also, like, at least in the continuum, I see no obstruction to playing with the Higgs mass parameter and making it larger positive. Anomalies all still cancel. I mean, there's nothing wrong. I mean, that's not our world, to be clear, because we have a Higgs mechanism operating. But you could imagine, you could easily just like change one potential on the SM and turn off phasing, realistically speaking.
Well, suppose you didn't have the Higgs.
Yeah.
You would still be able to form bound states of, the pions will play the role of a Higgs in that case. It just gets the wrong phenomenology. But the pion is there, and it's. I think you really need this Higgs to get the phenomenology to work right, because they have.
Well, my question is more about the theory. Like, I guess I'm confused. So are you saying that the QCD physics will gap out the W and Z bosons by itself?
Yeah, they will generate a W and Z
Very,
with
very
the
small.
pion.
Very
Yes.
small. It will be very, very small, but they will.
It doesn't drive things to the heavy mat. Well, we know the Higgs is pretty heavy.
I see. But in the limit that we start playing this game, do your doublers start trying to come back down? Or not? Do you rely on the sizable Higgs web to keep them?
Well, at this point, the actual masses are tuned parameters because there's this additive normalization with Wilson fermions, and it's just there. So we have to tune the mass coupling to get it right.
Uh-huh. I see. Thank you.
I can give you the slides too if you want. Okay, so there's a way to do this with the weak bosons too. And now we come to this topology business. There's kind of a discontinuity in the discussion here. Most lattice formulations have a gamma 5 hermeticity. You can get B dagger by just multiplying by gamma 5 on both sides. There's one exception to that. That's the twisted mass people. But we understand what's going on with that. So in this case, this is still true. If this is true, all eigenvalues of the Dirac operator are either complex pairs or real. And that's true even for the free Wilson fermion case. So in the free Wilson fermion case, you have the mass that you're trying to tune to. And then all the doublers are shifted off to these other crazy places. Each one of these things represents the number of components of the momentum, which are pi. Because doubler whenever any component is pi times the lattice spacing, pi over the lattice spacing, or 2 pi over the lattice spacing, 4 pi. No, I'm sorry, all 4 components are pi. So this is free for the fermions. What happens when how do you get real eigenvalues? They're either, all the eigenvalues are either in complex pair or real. And with plain Wilson fermions, well, you might get 0 mode when everything just vanishes. But depends on your boundary conditions. So what can happen, and I discussed this with the overlap back years ago, a couple of these eigenvalues can start wandering around. They wander and they can actually fill up all these little holes too, in general. The two can collide and you get a small real eigenvalue and a large eigenvalue in the doubler region. So this way you can get real eigenvalues for the Dirac matrix. But on the set of real eigenvalues, Dirac operator on that set of eigenvalues commutes with gamma 5, which means gamma 5 and the Dirac operator can be simultaneously diagonalized on the set of real eigenvalues. This means the real eigenvalues can be sorted by chirality. You can have plus ones and minus ones. And what we normally call topology corresponding to have some excess of the small ones over the opposite chirality of the other far out. So on the lattice, if you have a real eigenvalue, small changes in the fields don't make it not real. They've got to come back and collide. But if you smooth the fields out, and Musher is giving criteria for how smooth they have to be, the one of them actually gets driven to zero and gives you the usual instanton. But on the lattice, they won't be exactly zero. They'll be something small. So this is how you get to the index theorem on the lattice. So, small eigenvalues. What happens if you do have a zero eigenvalue? Well, let's calculate the partition function. Integrate over the gauge fields, integrate over the fermion fields. The integral of the fermion fields gives you the determinant of the Dirac matrix. And the determinant of the Dirac matrix is the product of all its eigenvalues. So what if an eigenvalue is zero? Well, it doesn't contribute to the partition function. So you would think you can just forget about zero modes. Are they irrelevant? Well, Till showed that that's not true. You can enhance them. So let me give you a real quick summary of what Till told us back in mid-70s. Take your partition function and add some sources to the theory. So you have your original partition function, but then you have a source for the antifermions and a source for the fermions. And then we can still do this integral. We just complete the square. And you get the partition function with the sources as a determinant, the source with the d to the minus 1. You still get the product of the eigenvalues, but you got a matrix in here which is the inverse of the Dirac matrix. The inverse of the Dirac matrix can get very big if you have a very small eigenvalue. And so this can cancel the suppression of the small eigenvalue. Now, for the strong interactions, this is pretty well known. It winds up generating things like the eta prime mass, which you can kind of understand by taking a u bar u and creating pi eta prime and destroying them with a d bar d. But the eta prime is not degenerate of the other two. And because it's not degenerate, this does not cancel. This does not vanish. So this is a process which flips the spins of the various constituents. Now this, well, this is actually a very interesting process, but I'm not going to pursue too much here, although you heard me talk in LA about this, and it has some interesting consequences. Among them, the fact that vanishing upquark mass does not really solve the strong CP problem, because it gives a mixing between the downquark mass and the upquark mass. I'm going to leave. Maybe I won't finish all that much early. So the weak interactions, it gets kind of interesting. because for each doublet, I can take and construct the conjugate, the antiparticle doublet, which is basically you take psi mu tau 2, a gamma 2 and the tau 2 on it, and then you get the antiparticle after conjugating. And of course, for each one of these things, it's right-handed. So the right-handed neutrino is there, and it has the opposite. I mean, it still couples. So what we can do is take each one of our 4 doublets and pair it up with an anti-doublet with a conjugate. And you can do this in a nice symmetric way if you anti-symmetrize over the 4 doublets. So you take 2 of your doublets, take the other 2 and conjugate them, put a D inverse in there. You can get a non-vanishing contribution to this because D inverse can flip the spins. And the epsilon keeps the SU3 symmetry good. And, but this is interesting. This is a 4 fermion vertex, which changes baryon number by 1 and lepton number by 1. So it preserves B minus L. In the Hamiltonian language, and I'm talking here in path integral language, but in the Hamiltonian language, what it corresponds to is some modes crossing in and out of the Dirac sea. So some fermion in the Dirac sea comes sliding up to become physical. Fermion number actually changes by 2 because we've got the 4. Anyway, it's consistent with SU2 because of the pseudo-reality lets you mix the antiparticles with particles. It's consistent with SU3 because if I take an anti-quark and turn it into 2 quarks, there's a singlet in 3 times 3b times the 3 bar. And there's a 3 bar and 3 times 3. So you can turn, you don't violate SU3 anywhere here.
And so this is a dimension 6 operator, you said? Can I think of it that way? And so
I don't
expressed by
usually
some-
think that way, but I think you're probably right.
You see, it's non-local because D minus
it's
1
non-local.
in the middle.
It's non-local, definitely, because
So
it's not has a size
basically
to
you
it.
are back to dimension 4, but it's a non-local operator.
Oh, okay, yeah.
And this, of course, is what Toof pointed out back in ancient past. So this 4 fermion interaction is actually effectively a mixing of the anti-neutron with the neutrino and the antiproton with the electron. So things like a proton decaying into a positron and a pion are allowed processes, except they are extremely small and they require a weak instanton, which has got e to the minus 1 over alpha with various factors in there. Much longer than the age of the universe. All right, I think I'm kind of, I'm a little early, but I guess that's okay. What 10 minutes, not too bad. It is possible to put 1 generation of fermions onto the lattice, keeping these symmetries exact, but it does require including a full generation, and it also requires there being a small amount of baryon and lepton number violation. And I haven't added any parameters to the usual continuum discussions. The fermion masses are parameters here. The gauge couplings are parameters. Higgs potential is another set of parameters. And there's a cutoff buried in there because all the doublers have been driven up to the cutoff, but no new parameters beyond the usual standard model. And I think that's all I have here. I do have some interesting questions which I haven't completely resolved. You've got weak instantons and you've got SU3 instantons. Are they really independent things? This goes back into, there's associated with instantons, there's this theta parameter. Now, it looks like there's going to be another theta parameter from the weak interactions. Are there any other angles hiding in here? I don't think so, but I would like to understand that better. And then if you go to something like SO10, there's only one kind of instanton. So I'm a little confused on how many thetas there are. And when you have one of these modes, how can you separate these zero modes into things associated with the weak and things associated with the strong, or do they get entangled when you have both fields around?
As far as I remember, there is no theta for weak SU2. Do you remember? There was a paper long ago in the early 80s by Anselm and Johansson. And they showed that SU2 is, I mean, you can get rid of theta.
That's an interesting question,
SU2 theta.
Because normally theta
I think it's because the right-handed neutrino is a singlet, so you can get rid of the phase in the mass term because the right-handed neutrino doesn't transform under SU2 weak.
That's true. If you think that it
Yeah, so
has
so
a
I think
mass,
that,
then,
yeah.
but it has.
But that's
to
where it
have-
would show up, right? The phase
Yeah.
would show up in the
Yeah.
mass term.
That's
So-
why you can rotate it away.
and you can rotate it away with a field which doesn't transform under SU2.
Yes,
So I think that's the same.
yes.
Of course, here I have to have a mass. And
So why do you say that the theta from the SU2 is physical now? You're saying that it's physical in your cell?
Well, I'm not sure. This is where I get in a little trouble now. In lattice language, for the strong interaction, theta is in fact equivalent to a phase of the Wilson term. It's a phase between the Wilson term and the mass term. And now, of course, we've got 8 fermions, so we've got 8 possible phases. Now, usually you can rotate them all into one. So the usual theta, you can rotate it into either the up or the down quark, or you can even rotate it into the top quark if you want. And they're all equivalent. So now the question is, how, with the additional doublet in there, can you rotate the SU2 one away? I don't know. I think that's an interesting question to be thought about.
May I ask another question?
Of course.
You're right, I don't know much about lattices, but I know enough about doublers.
Okay.
And they originally exist in your model. But
Yes.
then you said something very quickly that Higgs allows you to send the doublers to make them very heavy.
Yes,
I
that's
didn't get how this happens.
so basically you add to your term a psi d squared psi,
Yeah.
and d squared when you get to very high momentum is a big number. And so, and then you have to, but it's always a 1 plus a gamma mu in there. So that's where the tuning has to come. You basically separate the doublers from the non-doubler, and then you've got ability to shift. In the Wilson game, this mass has to be tuned to be 0. There's nothing natural about it. You can shift this thing back and forth with your parameters. And so these are all proportional to 1 over the lattice spacing or something. So
Yeah, but how Higgs helps you to do this fine tuning?
because you need
to
to.
get a way to get rid of these light doublers.
It comes about because you use the same mass term for both the Wilson and the physical mass. And so you have to tune, you can take this whole diagram with all the loops and shift it around, but there's no symmetry between M and minus M. And that's actually a physical statement. In perturbation theory, the sign of the mass is irrelevant. But in physics, it's not, because if the up quark is a little bit negative and the down quark is a little bit positive, you can still have masses pion. Actually, well, that was the subject of my talk in LA.
That one might be a related question.
Hmm?
I don't know if this happened.
I
I have a related question, I think.
Oh,
So, as far as I can tell, nothing bad would happen to what you're saying if you had either 7 or 8 generations, right? All the generations, for the sake of argument. Of course, that's not true. We don't have that in the real world.
Well, it has to be even though, I think.
No, generations.
Oh, generation.
1 generation is enough to make everything work here. Well, let's just make
In
it.
some number of generations, you lose asymptotic freedom.
That's the reason that I'm asking.
So,
So good. So I have a reason for picking on 7 and 8, okay? Because if you go to, let's say, 7, that's an F equals 14 from the point of view of QCD. And that is, by every expectation, in the conformal window. So in that situation, there are no QCD condensates, right? You're flowing to a CFT as far as QCD is concerned if the UCAVs are turned off. And now you can ask, okay, what do I do with the Higgs? I can go out in the potential and go to the regime where the Higgs is turning off. And everything should still be consistent. You should have a chiral gauge theory that is well defined, has all sorts of Hooft anomalies and whatever. But for your setup, I think this is, I don't know how you would deal with this because for you the Higgs is so important.
I would say that once you've lost asymptotic freedom.
No, I'm not losing asymptotic freedom. This is
You run
asymptotic
at the
freedom.
edge, you get which the edge of the conformal.
16. It's 16. I'm talking about 14. 14 flavors, not 16 flavors.
But
It's
it's already,
Benzac.
it's still in the conformal.
It's in the conformal window, but it's asymptotically free. It's IR conformal, not you. It's asymptotically free, but it's like a Benzac type of thing. It's a well-defined quantum field
It's
theory.
weakly coupled theory,
Yes,
which presumably
Yes.
nothing bad happens.
presumably nothing bad happens to
Nothing
any of this.
non-perturbative really happens due to
That's
SU3 gauge boson.
That's right. And the SU2 gauge boson should still be as weakly coupled as ever. But the point is
It may be a phase transition. It should be a phase transition.
yes, I agree.
Between non-conformal and conformal phases.
I completely agree, but I guess the reason that I'm pushing on this, okay, is that I find it surprising for the Higgs to be so involved in the consistency of the theory. Because to me, I somehow always thought that the Higgs is something we need for pheno, but not something we need for consistency of the quantum field theory itself. And one argument for why that should be true is what I just said. You can go to the conformal window, there's no self-Higgsing by QCD, and then I can get a phase where the Higgs is infinitely heavy, and you can forget it, and everything's consistent.
Oh, but there should be a reason why our world is constructed in the Higgs phase.
Well,
Because of course you can imagine a theory in the conformal regime,
Yes.
in the infrared. In the conformal regime, nothing exists. Because there are no localized objects, so no galaxies, no planets, no nothing.
right.
No masses there, right?
No masses, yes.
Well, okay, so then the idea would be that the fact that this doesn't seem to work in that regime
Yeah.
would mean that that's a reason for why we don't live in that world.
Well,
Okay. Fair enough, okay. I don't know what to say to that.
no, you see, I don't know what to say. In principle, you are right. In our theoretical laboratory, nobody precludes us from considering
Yeah.
7 generations
Yeah.
or 8 generations with everything very alive.
Exactly.
But Higgs regime doesn't work in this, right?
Exactly. But that's the thing, I mean, I've never heard of any reason to think that there's some conceptual problem with the well-definedness of such a thing, merely that, okay, that's not the world we live in, but it's a well-defined quantum field.
Well, it would be a conformal thing, and so there'd be no masses. So,
Yeah.
I don't know.
But it should be well-defined, right? At least I thought it should be.
I'm not quite going to say that since nobody's ever really defined a non-interaction field theory precisely. But
Maybe it's not accidental that you need Higgs in order to make theory definable on a lattice, which it means. After all, it's not yet fully because defined. It defined it is defined because the infrared freedom for Higgs and for U1, right? Or Landau pole, let's say. You cannot put the lattice size to 0.
we don't know how to do it. No, exactly.
Sure.
The Higgs
So
kind of
it's a limitation. Okay, it might work, say, until you make it Planck size. because it's still below, orders or hundreds of orders of magnitude below the Landau zero, all countries are still small. But in the mathematical sense, you still cannot make it fully continuous. It's approximately continuous.
Okay, fair enough. I mean, the reason I'm pushing on this is just to understand how far is this proposal going? So,
Yeah, but so if I can, because I'm also trying to understand the role of the Higgs here, because QCD itself breaks electroweak symmetry, right? So why can't I decouple the doublers just within QCD? I mean, you're using the Higgs to decouple them, but does it?
I think
within QCD, there's also a mechanism to give fermions.
there is, but I think.
But do you need another parameter? Is that?
You need, phenomenologically with perturbation theory, they have values for these expectation values, and they don't seem to be able to make the 4 Higgs coupling vanish. And so it's not consistent with perturbative phenomenology. So you really need to have this Higgs in there. At least that's what Sally Dawson tells me. You can't make the coupling. It would be nice if you could just make the 4 Higgs coupling 0, and then maybe you're better off.
But I guess I'm asking more of a theoretical question, just within just studying it on the lattice. Just if I was studying a world just with pure QCD, couldn't I decouple the doublers without a Higgs? That's the problem that you're solving, right?
Well, it's one of the traditional problems with the lattice, because you have these extra degrees of freedom. I think.
But you're adding a Higgs to actually solve the problem, right? That's.
Yeah. It's kind of like you could have the Higgs be some confined particle of some heavier quarks or something. That's the other way to do it. If you had another gauge group to give you the Higgs as
well,
a
there'd
bounce.
be say Technicolor, right?
Technicolor, good old-fashioned Technicolor, yes.
See, I mean, could you, because Technicolor would give sizable masses to the fermions, right? But
I think the phenomenology has never worked with Technicolor,
of course,
but in principle, yeah.
But in principle, like to decouple these decouplers, could you do it without a Higgs? Maybe have another strong group that plays that role? This is what you said in the beginning with composite Higgs, I guess.
Yeah, it could be, but I'm trying to stay within the standard picture so as much as I can. But you're right, you could have a composite Higgs, and then the U1. Well, you could solve that with a unified, which is why SO10 is such a pretty theory. Actually, it's got all the features.
Okay. Any other questions for Michael? Well, Michael's going to be here the rest of today, so if you have any more questions, feel free to stop by his office. But let's thank him again. Thank you.
Your question is very question, but
I could have tried another approach, which is stick with one generation and mess with the Higgs potential. And then you could.
By the way, sorry, if
the
anybody's
Higgs mass
interested in the
parameters
dinner,
such that
just let me know if anybody wants to join.
the way that it wants. So as you play with that, right, there's a kick to the Higgs vector in one direction, essentially. And QCD gives it a kick in a potentially different direction. So you could wonder whether you could tune the Higgs Web to 0. I know that Web doesn't make any sense.
Well, it's a gauge.
It's gauge. Yeah.
So you can't make it 0, but you could.
I don't know where it's to.
There's one opinion. There's some way you can get
Sorry,
it
Michael's-
self-coupling.
Sorry, Michael, just in